In the present video, we're going to discuss the use of units when developing equations that are going to be put in a graphics. We're going to repeat the case of the graphical solutions to equations when units are included. For that purpose, we're going to go to this SMath Studio worksheet in which I'm going to review a little bit what we did in the last class. We presented this problem of a pump pumping from a lower reservoir to a high reservoir, and we came up with two equations. This is an auxiliary function. The two equations are given by this and this. In this particular case, all the variables used, all the known variables actually, were used without units. If there is any reference to units, it was with like text next to it. And we were able to produce these two functions, HP1 of Q and HP2 of Q. And when we plot them, we get these results where the actual values of the Q are not, they have no units and the head have no units, although in the labels we indicated the appropriate units. Now we're going to repeat the same thing, but this time, same problem. We are going to add units to all the known variables used. The sum of minor loss coefficients is dimensionless. And the case for the pump equation requires us to use these appropriate units for the coefficients. Now we are using a unit that hasn't been defined before. That's the cubic feet per second, CFS. And what we did here was to type quote CFS, quote CFS, colon, quote FT raised to the cube, FT raised to the cube, space bar divided by apostrophe S. And that way we have defined this unit called CFS, which means cubic feet per second. Again, we're using units of the imperial system, which is commonly used in the United States. And so we define the function for the friction factor. We're using the same one that we used before because this ends up being dimensionless terms. Okay, K is it was called the relative roughness, which is dimensionless, and R is the Reynolds number, which is also dimensionless, and so we don't worry much about units there. But after we have defined our two functions, if we try to evaluate them using an argument which has no units, we get a problem because the units are not going to match. Instead, we need to put the appropriate units in the argument. So in this case, for example, 0.05, we use 0.05, quote CFS. Quote CFS. And it gives me the result in the default units, which are units of the international system. I tried the same here with HP 0.05 CFS, HP2. And then I have to change them to feet. I'm going to show you how to do that. You're just going to copy this, Control C, Control V, click everywhere else, somewhere, sorry. Click on this placeholder and type quote CFS, type let me try something here. Quote CFS. No, it isn't cubic meters per second. Oh, of course. I'm sorry. It's meters, not cubic meters per second. This should be just feet. For a moment, I thought I had messed up with the units. And the same thing here, you know, if I copy this result that is giving me units of the international system, and then I click to the right and click on the placeholder and type quote CF, I can't do it again, FT, feet, 1.52 feet. Now, suppose that I just type my graphic or insert the graphic. I'm going to repeat the step here. We're just going to click here and then go insert plot, XY plot. Then we go to the system of equations, so system of values, and type HP1 of Q. And then we're going to, because we want this Q to have units of CFS, we're going to say times what CFS, and then HP2 apostrophe quad time quad CFS. And it gives me the narrow value. We're going to modify the x-axis to go from 0 to 0.05 in increments of 0.01. And for y, we go up to 16, I believe. And so the maximum will be 16, minimum will be 0, in increments of 2. Okay. Now, increments, okay. There you go. We're not getting the graphic that I want. And that's something that you need to be aware of. In the last example, we have something similar. What you have to do here in this case is simply go to calculation and do recalculate page. And then you get the graph. But what we're seeing here is that the intercepts of 4 of 2 are not near the intercepts of 6 and 14 that we had here. What's going on? Well, let's check this. Let's calculate the heads of for 0, just to get our intercepts. I'm used 10 to the minus 6 here because if I try to do HP1 of 0 quad CFS, it gives me a division by 0. And the reason is that in the function, I do have a Q value somewhere in there that is not going to give me the proper results. Particularly, I think it's in this function as FSJ. If we look at the FSJ, indeed the K value is epsilon over D, and the Reynolds number R is actually V times D divided nu. But it goes into the denominator, and so when we get a 0 discharge, we get a 0 velocity, and that's going to blow up. So I cannot use 0 exactly, but I use a small value, 10 to the minus 6, and if I could try with like 10 to the minus 10, for example, if I want to, and gives me the same result. Now, in the original graph, we have 6 for the intercept for HP1 and 1409 for the intercept for HP2. If I divide by the corresponding values that I'm getting here, I'm getting as the ratio of 3.2802, which happens to be the ratio of 1 meter to 1 feet. Basically, what I'm saying here is 1 meter is equal to 3.28 feet. Okay, but I'm not getting that result in here. So what do I need to do? I need to scale out my functions and divide them by feet. And when you get that, the absolute number that you get here will be actually be representing feet. And so this is something that you need to be aware of when using units in graphs. Make sure that the function that you're going to plot has the proper units for the independent variable, and then that it is scaled to the units that you want. Basically, what's happening here is that you're getting your values in meters, because by default, SMAT Studio tends to give you units of the international system.